Welcome back to the lab. Now, a few days ago, I was watching a TV program about a guy trying to build his own cabin in the woods. He was using a single pulley to try to lift logs up on top of his structure. It's obviously he didn't have appreciation for the concept of work and mechanical advantage using pulleys. So that inspired me to create this episode of LabRat Scientific. So what we want to talk about today is work and mechanical systems such as spring systems and pulley systems and how work comes into play. So let's go ahead and get started by looking at the basic concept of work.
So what is mechanical work? Well, work is done when a force is applied over some distance. And the equation is work is equal to force in newtons times distance in meter. And so the units of work is Newton meters. Now, the force can come from any number of sources: gravity, wind, pressure, springs, all sorts of things. And work also has direction. And work can be either positive or negative. So work is positive when the force acts in the direction of movement. And work is negative when the force acts against the direction of movement. Now here's an example. Larry's trying to slow down this ball as it moves down the ramp. So gravity is performing work to make the ball move down the ramp, but Larry is trying to oppose the motion. And hence Larry is applying a negative work to the ball to keep from rolling too fast.
Now let's take a look at some pulley systems.
Here we have two simple pulley configurations. Now, pulley systems can be used to gain mechanical advantage. Now, while configuration A at the right can be used to lift an object, it provides no mechanical advantage. Configuration B can also be used to lift, but it also reduces the force needed to lift the object, thus providing mechanical advantage. Now, to understand how mechanical advantage is achieved, we need to examine the work done on the block. Here's our pulley system. If we assume the weight is acting downward, and that's mg, it creates a tension in the string, and that string has to pull upwards to keep the block from moving. And that force is transmitted through the string, over the pulley and down. Finally, we pull down on the string. Let's assume the weight of our block is 4.4 newtons. So if we want the block to stay still, we have to apply a 4.4 newton upwards. That means we have to pull down on the string with 4.4 newtons to keep the system in equilibrium. Now for this pulley configuration, every centimeter the string is pulled down, the block moves up 1 centimeter. And since we have to pull on the string with a force that's equal to the weight of the block, we don't realize any mechanical advantage. Now, if the downward force applied to the string is equal to the weight of the test block, the system will be in static equilibrium and nothing will move. If there's no motion, in other words, no displacement, there is no work done. Now, to get the test block to start moving, the string needs to be pulled with a force that's at least slightly greater than the weight of the test block. This creates an unbalanced net force, which accelerates the test block upwards. And this is F equals ma. So, if I apply a force downward on the string that's slightly greater than the weight of the test block, I can get the test block to move upwards. Now in this particular pulley configuration, the distance the block moves up is exactly the distance the string is pulled down. Now to simplify the assessment, we will just look at the system in the initial state and the final state. Here's the pulley system in its initial state, and here's the pulley system in its final state. Now when we do this, we don't have to concern ourselves about the unbalanced forces needed to accelerate or decelerate the test block.
Okay, before we mathematically analyze a pulley system, let's do a simple experiment to get an understanding of how the pulley will behave. Here's the weight of our test block. About 4.4 newtons. Here's my test setup for the single pulley system. Now each of the hash marks on the pulley frame are 2 centimeters. So I pull string through the pulley, 2, 4, 6, 8, 10, 12, 14, 16 centimeters. We see the weight raises 16 centimeters. So the distance the weight goes up is exactly the same as the amount of string I pull through the pulley. Now here's a force in the string for the single pulley system required to suspend the 4.4 Newton test weight. As you can see, the force is approximately 4.4 newtons. Now, in making these sorts of measurements with a pulley system, there's a potential for friction to corrupt your data slightly. So be careful when making your measurements. Now, I had to pull on the string with a force that was equal to the weight of the test block. And I also had to pull 16 centimeters of string through the pulley in order to lift the test block 16 centimeters. And that tells me there's no real mechanical advantage in using a single pulley system. Now let's take a look at the math and analyze this particular pulley.
Now let's analyze the simple pulley system. Here's our pulley, and you see the initial and final states of the test block. Now we pulled down on the string with a force of 4.4 newtons. So this is the tension in the string. And that force caused the test block to move upwards 0.16 meters. The work done by the string force while moving the test block from point A to point B is calculated as follows. Work is equal to 4.4 newtons times 0.16 meters, which equals 0.7 newton meters. Now again, this is the work done by the string pulling up on the test block. However, this is not the net work done in the system because we also have to look at the block and the weight force. You can't forget that gravity is pulling down on the block even though it was moving upwards. This is where the direction of work comes into play. Now, we pulled down on the end of the string and the string moved downwards. However, we need to keep in mind that when we pull down on the string, we're also pulling up on the block. So the force is actually in the direction of motion of the test block. Now, since the work was done in the direction of displacement, this work is positive. However, on the other end of the string, the way the block was pulling downward, yet the block was moving upwards. Since the gravity force acting on the block was in the opposite direction of the displacement, the work done by gravity is negative. We see that here. Work is 4.4 newtons times 0.61 meters. Again, that's 0.7 newton meters, but the sign is negative. Now, to understand the total net work on the system, we have to look at both the work done by our hand pulling downward and the work done by gravity. So the net work is equal to the work of our pull plus the work of gravity. Substituting our values, we see that the net work on the system is 0 newton meters. That's quite interesting. The net work performed on the block by the string force and gravity is 0. Now, we should keep this net work concept in the back of our minds, but in reality, we are usually concerned with the amount of work we must perform when moving something. As such, for the remainder of this lesson, we will only concern ourselves with the work done by pulling on the string, which then pulls on the block. So here's something interesting, a student thought experiment. How does the concept of net work apply to a block being pulled from point A to point B on a horizontal, frictionless table?
Now let's take a look at a slightly more complex pulley system, which actually provides some mechanical advantage. Now this is where you'll see the concept of work coming into play.
Here's a slightly more complicated pulley system that gives us some mechanical advantage. You notice it includes 2 pulleys. There's actually 2 strings holding up the test weight. Now, a free body diagram, or an FBD, is used to help us analyze more complicated systems. The FBD depicts the forces acting on a body. In this case, we'll be looking at the forces acting on our test weight. Now, the tension, or the force in the string, can be assessed by drawing the FBD of the block and the 2 ropes attached to it. So here's a picture of our test weight. We got 2 upward forces and the downward weight mg. Now, the upward forces will be equal to one another. Now, if we assume the system is in static equilibrium, i.e. the forces are balanced and the block is not moving, we can say the downward force is equal to the sum of the upward forces. So we have downward forces are equal to upward forces. We know that the weight of the test block is 4.4 newtons, so that's equal to force 1 up and force 2 up. Now, since force 1 is equal to force 2, we can rewrite the equation to say 4.4 newtons is equal to 2 times force up. And so the force up becomes 2.2 newtons. Now, if we redraw our free body diagram with the forces, we see that we have 2 forces upward at 2.2 newtons and 1 downward force at 4.4 newtons. And those are equal and opposite. Now, the diagram shows that the tension in the string is 2.2 newtons everywhere along the string. This analysis tells us we can lift a 4.4 newton block by only applying a 2.2 newton pull on the end of the string. Now actually, to get the weight moving, we're going to have to apply a force that's slightly greater than 2.2 newtons. We're not going to worry about that at this point. Now let's look at the work. As the simple pulley system shown earlier, let's pull on the string to lift the block 0.16 meters. The question is, how far down in the string do we have to pull in order to raise the block 0.16 meters? Now, the work done is the amount of work that is required to lift the block 0.16 meters. Of course, work is equal to force times distance. Now, regardless of the pulley configuration used, if we raise the block the same distance, the same amount of work will be done. As such, the work for the simple pulley is equal to the work for the complex pulley because we're lifting the same block the same distance. With a more complex pulley system, we determine that the pull force that needs to be applied to the string is only 2.2 newtons. Now, if the work that must be done is the same in each case, we're going to have a greater distance associated with the smaller force. So here's our two pulley systems. Simple pulley on the left, you see that work is equal to 0.7 newton meters. And the work on the right is still 0.7 newton meters, but it's 2.2 newtons times some unknown distance. Once again, here's our work equation. We see that 2.2 newtons times some unknown distance is equal to 0.7 newton meters. We apply a little bit of algebra, so we see that distance is equal to 0.7 newton meters divided by 2.2 newtons, giving a distance of 0.32 meters. This tells us that we need to pull on the string 0.32 meters in order to raise the block 0.16 meters. So when we have the required pull force, the distance over which we have to apply that force is doubled. This makes the work the same.
Now let's take a look at a second experiment to see if this is actually what happens. Now here's the force required in the string, or the tension in the string, required to suspend the 4.4 Newton test weight. We see that the force is approximately 2.2 newtons. Now let's look at how much string needs to be pulled through the pulley system to raise the weight 16 centimeters. Now each of the hash marks on the rig is 2 centimeters. So there's 16 centimeters of string. We see the weight's gone up halfway. And there's another 16 centimeters of string, and we see the weight has been lifted 16 centimeters. So we required 32 centimeters of string to be pulled through the pulley system to raise the weight 16 centimeters. From that experiment, you can see that I only had to pull on the string with a force that was half that of the weight of my test block. I only need to apply a 2.2 Newton force to raise the 4.4 Newton block. However, I had to pull twice as much string through the pulley in order to raise the test block the desired 16 centimeters. Now let's take a look at the force distance diagrams to determine the work that was done for each system.
Here's a graphical representation of the forces involved with our two systems. Here's our simple pulley system. We see we had to apply a 4.4 Newton force to the string to suspend the weight. In order to move the weight up 0.16 meters, we had to pull 0.16 meters of string through the pulley system. Now here's our more complicated pulley system. And we had to pull on the string with a force of 2.2 newtons. But in order to raise the weight, the 0.16 meters, we had to pull 0.32 meters of string through the pulley. Now the area under the force curve is the work that was done. And notice the area in each of these diagrams is the same. The simple pulley system, the area, which is equal to the work, was 0.7 Newton meters. And the area and the work for the more complex pulley system was also 0.7 Newton meters. So in conclusion, a pulley system can be used to reduce the amount of force needed to lift an object, but the amount of work that needs to be done remains constant with respect to lifting a specific load to a specific height. We can apply that conclusion to this more complex pulley system. So we have multiple pulleys and 4 strings supporting the test weight. Now if we assume the same test weight as before of 4.4 newtons, we see the string tension is only 1.1 newtons. That's 4.4 divided by 4. So we only have to pull on the string with a force of 1.1 newtons to lift the weight. Now, if we want to lift that weight 0.16 meters as before, we see we have to pull 4 times the amount of string through the pulley to raise that weight. The work is constant. However, the force required to lift the weight is smaller.
Okay, now let's take a look and see how work comes into play with mechanical springs.
Springs are governed by Hooke's law. And Hooke's law is used to calculate the force generated by the compression, extension, or bending of a springy object like a rubber band, a spring, or even a flexible rod. Hooke's law is expressed as follows. Force is equal to spring constant times distance, or force is equal to kx, and units are newtons per meter times meter equals newtons, which is the units for force. So here's our spring. The top spring is in its relaxed state. The force is 0 because deflection is 0. We compress the spring a certain distance x. We can calculate the force being applied by that spring by applying F is equal to K times X. The spring constant K can be determined by applying known forces to the spring and measuring how much the spring stretches. Here's a relaxed spring. It's have 0 deflection, so it's 0.0 meters. We apply a known force to the spring stretches, and we say it stretches 0.1 meters in this case. Plot that on the graph. Apply more weight, measure deflection, and plot that. Now, if the force curve is linear, the slope of the line represents the spring constant K. Now we can determine the spring constant. That's equal to the slope. Slope is equal to rise over run. We'll pick this point. The slope is equal to 2 newtons divided by 0.2 meters. And the slope is 10 newtons per meter. And that means the spring constant K is 10 newtons per meter. Now let's take a look at the work done by a spring. Here's our force versus length graph. And the area under the force curve represents the potential energy of the spring. So if we calculate the area under that curve, or the area of that triangle, we see we have applied force in newtons times stretch length in meters, so the units become Newton meters, and those are indeed the units for energy. Now, energy is the object's potential to do work, and work is the change in energy of the system. So this means that the area under the force curve also represents the work that is done when the spring is released. Now we can calculate the potential energy of the spring when it's stretched 0.3 meters using the equation for a simple triangle. That's 1/2 base times height. So the potential energy of this spring when it's compressed or stretched 0.3 meters is 1/2 times 0.3 meters times 3 newtons. And we see that the potential energy is 0.45 Newton meters.
Now let's do a simple pull test on the spring to see if this theory actually works.
Here's the pull test on the spring. I extend the spring, making measurements as I pull. I pull the spring to a distance of 10 centimeters. Here's the results of that simple experiment. I show 2 images, the spring in its unstretched position and its fully stretched position of 0.1 meters. The table at the right shows the data that I collected as I stretched the spring. Now plot that data here. You see the force versus the stretch length forms a relatively straight line, which forms a triangle. If I calculate the slope of that line, I come up with 115 newtons per meter. I can actually calculate the spring constant in every point along the stretch. You see I've plotted that here at the bottom. Now it's not quite linear or totally horizontal. That's due to little data errors as I made my measurements. However, they do follow a somewhat consistent 115 newtons per meter spring constant.
We've demonstrated that we can make some simple measurements on a spring and calculate how much work that spring can do. Now let's take a look at an experiment to see how the work produced by a spring affects the motion of a rolling cart.
In this experiment, we're going to shoot a cart down a track using a stretched rubber band. The first step will be to measure the force versus stretch length of the rubber band to determine the potential energy, which is the area under the force versus distance curve. The potential energy is the amount of work that can be applied to the cart when the rubber band is released. The work the rubber band does on the cart will make the cart move, which creates kinetic energy. So let's go ahead and measure the force versus distance of the rubber band. I have no stretch in the spring, so I have 0 force. There's 2 centimeters. 4 centimeters, 6 centimeters, 8 centimeters, and 10 centimeters. Here's the data. At 0 deflection of the rubber band, we had 0 force. And when I pulled the rubber band back 0.1 meters or 10 centimeters, we had a total force of 5.25 newtons. Here's the data plotted on a graph. We see it's not quite linear, but it's close enough to assume it's forming a triangle. Now, The slope of the line, or the slope of the top of the triangle, represents the spring constant of the rubber band system. And the area under the curve is the potential energy, and the amount of work the rubber band can do if it's released. If I calculate that area, 1/2 base times height, I get an area of 0.25 Newton meters, which is the work the rubber band can do. Now we can calculate the theoretical velocity of the cart after being pushed on by the rubber band. Now recall that potential energy is the work that can be done, and the potential energy is the area under the force versus distance curve. Now when we release the rubber band, that work is performed on the cart, and that work causes the cart to accelerate, thus increasing its kinetic energy. Now we can apply the work energy theorem, which states that change in kinetic energy of a system is equal to the amount of work done on that system. Mathematically speaking, work is equal to the final kinetic energy minus the initial kinetic energy, or the change in kinetic energy. Now if the object is initially at rest, the work energy equation becomes work is equal to the final kinetic energy. We know that kinetic energy is 1/2 mass times velocity squared. If we apply some algebra to that equation, we see that velocity is equal to the square root of 2 times the work divided by mass. We plug in numbers for our experiment, and we see the theoretical velocity of the cart after being pushed on by the rubber band is 1.12 meters per second.
Well, the big question is, will the cart achieve the predicted velocity due to the work that the rubber band applies to it?
Test 1, I'm going to stretch the rubber band to 10 centimeters. 3, 2, 1, release. Test 2, 3, 2, 1, 0. Test 3.
Okay, let's take a look at the data from that experiment.
Here are the final results from our experiment. We ran 5 trials measuring the velocity of the cart each time. We got an average velocity of 1.05 meters per second after the cart was pushed on by the rubber band. Here's a comparison between the theoretical and measured values. Theoretically, we calculated that velocity should be 1.12 meters per second, and experimentally we measured 1.05 meters per second. And this variation represents a 5% difference, which isn't bad considering the crude nature of our test setup. So I think this demonstrates that work performed on an object results in motion and an increase in kinetic energy.
Well, there you have it. My experiments seem to validate some of the basic physics behind spring systems and pulley systems. Now we can actually use these theories to make some predictions and to help us solve engineering problems. I hope I provided you some grassroots knowledge that helps you understand the concepts of works, springs, and pulleys. And I encourage you to do your own experiments to expand your knowledge and exercise your mind. Well, I hope to see you next time here at LabRat Scientific.